Welcome to this introduction to dynamics, which is the second course in rigid body mechanics. And now quickly reviewing mechanics here. Mechanics is a branch of physics concerned with the state of rest or the motion of bodies under external forces. And now the keyword here for this course is the motion of bodies, since dynamics no longer focuses on the state of rest. And of course we have three branches of mechanics, one being rigid body mechanics, which is statics and dynamics. So this is the branch that we're focusing on. And again, this means that we're not dealing with any deformation of bodies. And the other two branches are deformable body mechanics and fluid mechanics. And so what exactly is dynamics? Well, it is simply an area of rigid body mechanics that deals with the accelerated motion of dynamic bodies. And remember that the word dynamic refers to something that is constantly changing over time and therefore in motion. And now the key word here is accelerated, meaning that velocities are not constant. And also therefore we are no longer looking at equilibrium states at rest. So the summation of forces are ideally no longer equal to zero like they were in statics. And of course this means that this course is significantly more difficult than statics, since we're dealing with constant change over time, with a lot more variables and geometry, and also plenty of calculus in almost all the problems. So this course tends to require plenty of studying time as well as practice in order to feel comfortable solving problems. And now, why is dynamics important? Well, first of all, many engineering practices tend to face objects or mechanisms that are constantly in motion under the influence of external forces, for example, cars, airplanes, spacecraft, and machinery. And it is also important to be able to describe the motion of particles under certain conditions and analyze/predict the kinetic behavior of accelerated objects. So this is absolutely crucial for successfully developing and engineering products or systems that heavily rely on motion. So now for the first topic in dynamics, we want to start off with the concept of rectilinear kinematics, which is basically the motion of a particle along a straight line, which is the simplest motion for a particle. So now let's say we have a red particle starting at an initial point 0, and it moves horizontally along the x-axis to the right as shown. And let's say at this point in time, the distance from the initial position to the position on the right is represented by s, and the initial position I'll call s1 and the second position s2. And if the particle is moving, we assume it has velocity and acceleration. And now I'll go ahead and add a third position to the right of the second position. So this will create a new s variable starting from the second position to the third, as well as a total distance s prime. And now let's say that the distance between s2 and s3 is delta s, which represents the change in s, which of course will be equal to s prime minus s. And so, taking a look at a quick summary of the kinematics of a particle, the kinematics of a particle primarily deals with position, velocity, and acceleration. And keep in mind that a particle has mass but no size. So essentially the main thing defining a particle is its mass, its position, its velocity, and its acceleration. And now reviewing the concept of displacement back from physics. Displacement is of course simply the change in position of a particle. Keywords change and position. And so from the sketch we said that delta s represented the change in position or distance of the particle. So therefore it represents the displacement. And of course remember that displacement refers to the change of position with respect to an original position or reference point. And so here, delta S is equal to S prime minus S. So notice that both S and S prime are related to the original position 0 of the particle, since that's where they are starting from. And now keep in mind that displacement is considered a vector, since it is defined by both direction and magnitude. Like for example, for direction, displacement can be negative if a particle moves to the left or if it moves down. And of course, its magnitude is by how much or how far it moves. And now taking a look at velocity. Velocity is of course physically defined by the change in position of a particle over time. So let's say we have another particle here and it has velocity v, and this is position 1 and position 2 at times t1 and t2. So from this we can simply express average velocity as change in position s over change in time t. And of course remember that delta s, or the change in s, is simply s2 minus s1. And likewise, delta t is equal to t2 minus t1. And so once again, velocity simply represents change in position over change in time. And now looking at this from the calculus perspective, keep in mind that small values of delta t mean small values of delta s. And so hence, the instantaneous velocity v over small increments equals ds by dt. So as you can see, this is basically the calculus representation of velocity, which basically states that instantaneous velocity is equivalent to the derivative of position with respect to time, whereas simply delta s over delta t is average velocity. And of course, from calculus, this is saying that v is equal to the limit of delta s divided by delta t as delta t approaches 0, which is essentially ds by dt. So once again, remember that the derivative of position is simply velocity. So now moving on to another important component of dynamics, which is of course acceleration. So here, whenever velocity is known at two different instances, then we can mathematically define the average velocity as delta v over delta t, which is of course v2 minus v1 over t2 minus t1. And now in order to help visualize this, let's say we have a particle that is moving to the right, and let's say the velocity is increasing for this particle, and we have a second position or instance to the right, and this particle is carrying an acceleration to the right, and so we also have v1 and v2, just like so. And let's say this is moving along position s, or I guess you could say x, whichever variable you choose. And now to define acceleration, we of course need time on the two instances, so we have t1 and t2. And since acceleration is defined as the change in velocity over change in time, acceleration is essentially the derivative of velocity. But keep in mind that this is only when velocity is not constant, because of course there is no acceleration if your velocity is remaining the same, since basically v2 is equal to v1, which cancels out. And also from the calculus perspective, the derivative of a constant is just 0. And now back to our example, let's say that v2 is greater than v1, which basically means that acceleration is positive, meaning that the particle is speeding up. Whereas if v2 is less than v1, then our acceleration is of course negative. And well, here we can easily check this by substituting in numbers. So let's say v2 is 2 meters per second, and v1 is 3 meters per second, and t2 is 2 seconds, and t1 is 1 second. From this, we of course get -1 meters per second squared, which in this case, the particle is decelerating or slowing down. And now let's define instantaneous acceleration like we did with velocity. Instantaneous acceleration A is equal to dv by dt, where smaller values of delta t are related to smaller values of delta v. And of course, from calculus, this is acceleration A is equal to the limit of delta v divided by delta t as delta t approaches 0 is equal to dv by dt, which again is basically the derivative of velocity with respect to time. So to sum up, delta v over delta t is average acceleration, whereas dv by dt is instantaneous acceleration. And so from this, you should also note that acceleration A is also equal to d squared s over dt squared, which is of course the second derivative of position s. And also once again, keep in mind that if velocity is constant, that means that acceleration is 0, meaning that velocity is not changing over time. So for example, if delta v equals 0, where v is constant, that essentially means that v1 is equal to v2, so therefore a is equal to 0. Since, for example, average acceleration is equal to delta v over delta t, so plugging in delta v equal to 0, we have 0 over delta t, which of course is 0. Next, we want to take a look at the differential relation between position s, velocity v, and acceleration a. So we have found that velocity is equal to ds by dt, the derivative of position s over time, and acceleration is equal to dv by dt, the derivative of velocity over time. And now if we rearrange the velocity equation, isolating dt, we have dt equals ds by v. And now doing the same for acceleration, we have dt equals dv over a. And so from this, we can see that dt is equal to ds by v, which is also equal to dv by dt. And now if we cross multiply our terms and simplify, we have ads equals v dv. And so as you can see, after using some basic algebra, we have developed a differential relation between position s, velocity v, and acceleration a. And next, you'll see why this expression will be very useful for not only understanding the relation between acceleration, position, and velocity, but also integration between variables. So now taking a look at cases with constant acceleration, where a is expressed as a sub c. First off, let's say we want to express velocity as a function of time t. For constant acceleration ac, we know that acceleration is equal to dv by dt. So if we want to solve for velocity, we basically want to undo this derivative. So in that case, we need to integrate this expression in order to solve for v, because from calculus we know that integration is the antiderivative of a function. And since definite integration calls for initial conditions, we will assume v to be equal to v naught, which is v initial, at t equal to 0. So of course, before integrating, we want to first isolate dv. So we have dv equals ac dt, after simply multiplying dt to the other side. And so now we can take the derivative of dv from v naught to some arbitrary v, and then on the other side, the derivative of ac dt from 0 to t. So hence this is v minus v naught equals ac times t. And so solving for v, we get v equals v naught plus ac times t. And so that is velocity expressed as a function of time at constant acceleration. And this expression may be familiar from Physics 1 class. Here you can just see how it was derived using calculus. Next, we can also express position as a function of time for constant acceleration, following the same procedure as we did for velocity. In order to find position, we want to integrate velocity, which is ds over dt, and we just found that velocity v is equal to v naught plus ac times t, right from this expression above. So now, similar to before, we want to assume our initial conditions to be s equal to s naught at t equal to 0. So here we isolate ds, and we take the integral of ds from s naught to s, and then on the right side is the integral from 0 to t, and here I'll substitute in v naught plus ac times t for velocity. So now we can proceed with the integration. So integrating ds from s naught to s, we get s minus s naught, and that'll be equal to the integration on the right side from 0 to t. Here we have two parts being added together. So initially the integral of v naught from 0 to t is simply v naught times t, and now plus the integral of ac times t. So let's integrate that on the left side here. Using the integration rule, we get ac times t squared over 2. And well, when we check this by taking the derivative, we get 2 ac times t over 2, and the 2 cancels out, so we're left with ac times t. So hence this will be plus 1/2 times ac times t squared. And now isolating s, we have s equals s naught plus v naught times t plus 1/2 times ac times t squared, which is position as a function of time t. And again, this should be an expression you may have seen in physics class. And finally, for our third expression of constant acceleration formulas, we have velocity as a function of position s this time. So now, in this case, we're simply integrating that one expression we had found relating velocity, position, and acceleration, which is v dv equals ac times ds. Here, of course, I just substituted in ac, whereas before we had ads equals v dv. Now here we will assume our initial conditions to be v equals v naught at s equals s naught, where this basically says that velocity is initial velocity at initial position. Here, of course, we don't have a time t variable as we did before. So in that case, we're integrating v dv from v naught to v, and the right side ac ds from s naught to s. So integrating v dv from v naught to v, we get v squared over 2 minus v naught squared over 2, right? Because when you take the integral of v dv, that'll be v squared over 2. And when you take the derivative of that, of course, you're left with v, which checks out. And now on the right side, taking the integral from s naught to s of ac ds, that is ac times s minus ac times s naught. And so we can simply write this as ac times s minus s naught. So now simplifying this further, we have v squared minus v naught squared over 2 is equal to ac times s minus s naught. Now multiplying the 2 to the other side and adding v naught squared, we have v squared equals v naught squared plus 2ac times parentheses s minus s naught. And so that right there is velocity expressed as a function of position s, of course, at constant acceleration. And now one last important thing to remember is that these expressions are only true if and only if acceleration is constant, meaning that change in acceleration is 0, which of course means that the derivative of acceleration with respect to time is 0. So in summary, we have 3 different expressions at constant acceleration. And later on, you will soon see how these will be very useful for solving problems through examples dealing with acceleration, velocity, and position. And so that'll be all for the introduction to dynamics. I hope you learned many useful things about the relations between acceleration, velocity, and position, and also pretty much seeing how calculus is well integrated into this course. And thank you for watching. If you have any questions, feel free to ask in the comment section or join the Discord using the link in the description below. And if you found this video helpful, make sure to leave a like and subscribe for more.